Good morning, everyone. I'm Christian Zeyen. I'm a board director with OSEA, and I run a software startup called Oracle Lens. I'm also an industry partner with Humber College, where I mentor grad students in a number of different programs, AI, cloud computing, business IT, and beyond. And I also mentor and work with students at Ontario Tech University as well. So at Oracle Lens, our focus is on building software that helps save renewable energy and broadly energy and utility companies time and money in various different ways. Our main software offerings and services are time series forecasting and consulting, so using our custom machine learning models, many of which have never been seen in peer-reviewed research before and have outperformed globally, which I'll share a little bit about more at the end of this presentation. Designing and building exchanges for procurement, for cloud computing, GPU using decentralized ledger-based computational resource sharing. This reduces the energy requirements on data centers and the energy grid and lowers the cost to consumers by using this decentralized technology. We also have a material and commodity procurement exchange that we're building. And what I'll be talking about mostly today is a meter-settled marketplace for local grid flexibility that complements, not replaces, existing device controllers and VPPs, virtual power plants. So as I mentioned, today, the primary focus, distributed energy and our DE Flex, Ontario Flexibility Exchange. It's a neutral marketplace for forecasting and meter-based settlement for Ontario local distribution companies. So let's start with a summary. We are building here a neutral exchange where Ontario local distribution companies post location and time-specific needs and participants submit offers. Why this matters? Well, as many of you know, having inexpensive flexibility for peaks is a top priority. This is one of the main benefits of this exchange, as is better reliability and lower program and integration costs without changing existing controls. The operational control stays with the utility and the facility operators, and device data supports operations only. Settlement uses interval smart meter reads, and the meter is a single source for payment. Standardized transaction layer for tenders, offers, and settlement that cuts one-off integrations and contract sprawl while preserving the meter-based audit. So why now in Ontario? Well, local distribution companies need simple ways to activate flexible load and storage for local peaks and for feeder constraints. Ontario has province-wide smart metering, interval reads flow through the central meter repository, and customer authorized green button data is standard across Ontario utilities. Public agencies and boards require audit-ready evidence and clear privacy practices, which is something this exchange offers. Now, going into the program overview and the rules, we have a local distribution company where they post local needs, they set safety rules, they authorize program actions, they apply credit on bills. Then we have the facilities and the aggregators who enroll sites and devices, they submit offers, and they deliver within defined bounds. The program operator then runs enrollment, tenders and offers, baseline settlement, and audit records. The authorized market participant can package measured reductions for system programs when beneficial. Now, in terms of eligibility here, there's some customer types, for example, unit submetered or certain net metered accounts that will follow utility-specific rules and require LDC confirmation at enrollment. Now, going into the governance and the control boundary here, it's a utility-led program rulebook, so it includes roles, change control, and dispute paths. SCADA, which is supervisory control and data acquisition, and plant operators have override at all times for safety and service. The dispatch can be paused or capped by utility-based local conditions. Device telemetry supports the safe operations which are not used for payment. The neutral exchange, of course, standardizes tenders, measurement and verification, and settlement across vendors. Now, the Ontario data rails and settlement in particular here, I went over this briefly earlier. We'll go over this in more detail. The settlement will use interval smart meter reads from the provincial meter repository. The green button consent authorizes the sharing of interval data. The meter is, of course, a single source for payment, and device and gateway data supports the operations only. Statements and on-bill AP files are issued after each event, and a simple dispute path is included in case there's any issues. The baselines are published in plain language and reflect normal patterns for site and season. And if intervals are delayed or estimated, of course, utilities validated data and published rules win. Now, looking at the eligible flexibility product, so that which is integrated into the exchange to allow for this flexibility. So we have the data center flexibility, short UPS discharge and small cooling trims within service and temperature limits. That's one big piece. Water and wastewater pumping windows where they pre-fill storage and they trim during peaks within pressure and quantity limits. Municipal buildings that also have short trims with comfort safeguards, and EV managed charging, fleets and multifamily charging with customer choice respected. And the all-important data privacy and security is something we take seriously. So the customer's authorized sharing of interval meter data only through green button. Minimal data is collected. It's only collected for operations, for measurement and settlement purposes. And the security, encryption in transit and rest, role-based access controls, and documented retention timelines. The standard but important privacy and security pieces. Now, looking at the integration and operations, so the enrollment flow and beyond. So the enrollment flow links consent to site and device identities. The tenders define time windows, locations, and measurement methods. The offers specify capabilities and bounds, and confirmed offers create a short-form agreement. Dispatch instructions flow through existing plant systems or secure site gateways, and operators retain override. Post-event processing computes delivery from meter data and publish a statement for review. Now, looking at the pilot plan here, how we intend to go through the first phases, phase 1 to 3 with this. So step 1, phase 1 is readiness. We select a small number of feeders with recurring local peaks or constraints, and we confirm a small cohort of data centers, municipal facilities, and the like. Phase 2 is a live pilot. This is where we run limited events across enrolled sites. We settle for meter intervals. We collect operator feedback, and we publish plain language result briefs for boards and community partners. Phase 3 would be scaling, so adding sites based on measured performance and utility priorities, and introducing location-specific tenders, targeting recurring constraints. Now, what I'm going to do next is switch gears a little bit and talk about the demand forecasting piece and forecasting in general. This is our bread and butter at Oracle Lens. This is where we started with, and it adds in nicely to this marketplace, this neutral exchange, but it also has value to the renewable energy industry, the energy industry as a whole, and utilities for a few reasons, which I'll get into now. So let's start with the results. For electricity demand forecasting on the hourly time frame, we used here a model that was many of our models are the first of their kind, and again, not seen before in peer-reviewed research built in-house. So for electricity demand on the hourly time frame, aggregated 15 minutes into hour, it's the shortest time frame they have in the gold standard repository known as Monash, which I'll get into in a moment. Our Oracle Lens custom neural network achieved an MASE of 0.4809, and for those who don't know, lower is better, much like golf. That's a 69.92% improvement over the top performing benchmark models of all in this Monash time series forecasting repository. A 78.77% improvement over Google's Times FM, and a 76.54% improvement over Meta's profit model. So why this benchmark matters? Well, the Monash time series forecasting repository, as a background for those who don't know, it has data sets and evaluation rules which are managed by Monash University. It's a globally respected benchmark suite for comparing forecasting models, including machine learning, stochastic, and classical statistical models. And it does this across academia and industry. Now, note for this particular data set, as I mentioned, the lowest time frame that the repository offers for electricity demand is aggregated 15-minute readings into 1-hour data points. So outperforming all the benchmark models demonstrates state-of-the-art accuracy and under fair and rigorous conditions. So we follow blind test sets, no data leakage, and no pre-training on other data sets besides the training data set provided that all other competitors used. This Monash data set consists of well over 8 million data points aggregated from hundreds of sources and over several years. This tests our model rigorously and shows real-world generalizability. These high hourly forecast accuracy directly supports precise load planning, improved demand management, and efficient operations. So going a little bit more into the practical side of this, let's look at the operational efficiency benefits and some of the other benefits for the energy sector. So better forecasts improve scheduling and coordination across assets, reduces avoidable over dispatch, and last-minute interventions. More accurate forecasting enables optimized generation schedules and reduces unnecessary energy production. It also allows for enhanced grid reliability, improved demand predictions, support stable grid performance, and help minimize preventative curtailments and outages. In terms of cost optimization here, it enables smarter procurement, balances choices where applicable, and avoids rush premiums and unnecessary reserve calls. And for scalable real-world impact, these methods generalize across regions and asset types, which are modeling and testing as shown, without replacing existing controls. And of course, for our exchange, settlement remains meter-based. So one more thing I'd like to discuss before we go is one of our other models. So we also have a model that we've assessed on financial, industrial, demographic, and economic data. This is once again using the Monash forecasting repository, and we use the respected M3 data set, which aggregates each of these financial, industrial, demographic, and economic forecasts into one monster challenge data set there with millions and millions of data points. This uses MASE, much like the electricity demand, where a score of greater than 1 means worse performance than a seasonal naive benchmark, and less than 1 means greater performance than a seasonal naive benchmark. So the forecasting results are as follows. We achieved a blind test set MASE of 0.6793. This surpassed the top performing model, once again, of all benchmark models called TBATS. We outperformed them by 21.10%. We also beat Google's Times FM model by 30.9%, so over 30%. And we greatly exceed Meta's profit model once again, outperforming by over 50%. Again, once again, we follow the rules outlined, blind test sets, no data leakage, no pre-training, everything fair in that regard. So these results show that our models add tremendous value. They help our customers predict and adapt to demand growth. They help them it offers flexibility for peaks while reducing costs. It also reduces the time required to integrate new resources and beyond. It helps customers adapt to customer counts, predict interest rates, and importantly, forecast optimal time and price points in which to buy key infrastructure components and parts. It saves them time, it saves them money. It's broad, it's capable of handling forecasting tasks of a number of different types. So whether it's procurement, whether it's looking at how demographic changes will occur, how needs will change, supply and development within industry, all of this we've proven we can forecast on one of the most challenging data sets that they offer. So in conclusion, there are clear benefits to this neutral distributed energy marketplace. It offers flexibility for peaks while reducing costs and the time required to integrate new resources and beyond. As well, I hope you leave learning that there are much better forecasting models than those which are traditionally used by utilities, by renewable and regular energy companies, and beyond, manufacturing, et cetera. These, of course, add substantial value for saving money, optimizing procurement timing, and strategy. So thanks everyone for listening, and I look forward to speaking with all of you throughout the day. Have a great rest of your day.